this topic, we are going to study synthesis of nitroaniline. The synthesis of nitroaniline by using the green methods. So ortho-para-nitroaniline can be prepared by reacting the corresponding chloronitrobenzene with 25% ammonia at 170 degrees centigrade and 340 atmospheric pressures. In this case, orthochloronitrobenzenes, chlorine is at ortho positions and chlorine is the family of the halogens. So these families act as the good living groups. So some cases we substitute the hydrogen if they are present, but in case chlorine is present, chlorine is already the good living groups. So we can easily substitute chlorine atom by the ammonia atoms. So substitution reactions can be easily possible in the case of the chlorine halogen atoms present there. That is, NH3 replaces the Cl atom and their substitution at the ortho position, that is. So ortho-para-nitroaniline can be prepared by reacting corresponding chloronitrobenzene with 25% ammonia at 170 degrees centigrade and 330 to 40 atmospheric pressures. And next is the para-chloronitrobenzenes can be replaced by the NH3 ammonia 170 degrees centigrade at 30 to 40 atmospheric pressure. Replace the chlorine atom by the NH3 para-nitroaniline is formed. Methods. So in case of the COH NH2 means the anthracynilic acid, the reactant react with the NaNH2 sodium nitrite along with the HCl at the 0 to 5 degrees centigrade. Converted this NH2 into the N2 diazotization process takes place. Now N2 is the good living group. Convert that N2 group by the Cl means Cl is formed, orthochlorobenzoic acid is formed. Now this orthochlorobenzoic form is very chlorine is easily substituted by any reagent. Next is para-bromobenzoic acid. In the same case, we can replace the bromine atoms easily. And the CS3 group is the react with the KMnO4. KMnO4 is the good oxidizing agent that oxidize CS3 group into COH group. Next is the para-aminobenzoic acid. In that case also NaNH2 sodium nitrite react with the HCl 0 to 5 degrees centigrade temperature. Diazotization reaction takes place, convert into N2 which react with the COBr, convert that N2 into the Br, that is para-bromobenzoic acid is formed. Next is the synthesis of alcohol using the Grignard reagent. If the Grignard reagent reacts with the formaldehyde, then the primary alcohol is obtained. HC double bond H plus CS3MgBr react with the HCHCS3OH, that is the CS3CH2 primary alcohol. Primary ethanol is there, forms. Next question is how will you prepare the 3-methyl-1-butanol? 3-methyl-1-butanol by using Grignard reagents. So firstly, if I write down the structure of 3-methyl-1-butanol, this is the structure of 3-methyl-1-butanol. Starting materials we can easily find out, which react with the formaldehyde in presence of dry ether. S3O plus form will give the CS3CS, CS3CS2, CS2. mgbr. For the preparation of secondary alcohol, if the Grignard reagent reacts with any other aldehyde except the formaldehyde, then secondary alcohol is formed. Example: aldehyde CS3C double bond OS CS3 mgbr in a dry ethers form the oxygen magnesium complex. Acidic condition provided then that mgbr removes an OH bond form, that is secondary alcohol is formed. How will you prepare the 1-phenyl ethanol secondary alcohol by using the Grignard reagent? Here's 3 mgbr react with the benzaldehyde, use the mgbr CS3H2O. Tertiary alcohol, how will you prepare the phenyl 2-propanol by using the Grignard reagent? Acetophenol is the reacting material, starting material that react with the CS3 mgbr methyl magnesium bromide, form the CS3C-CS3O mgbr S3O plus and give the tertiary alcohol as the product. Synthesis of alkane using organolithium compounds. Synthesis of alkane using the organolithium compounds. Reaction with the compound containing acidic hydrogens. Organolithium compounds reacts with the water, alcohols, etc. to form the corresponding alkanes. Methyl lithium methanes reaction with alkyl halide. CS3Li, CS3Cl, CS3CS3 plus LiCl. CS3CS2Li plus CS3Br gives CS3CS2 CS3 plus LiBr. Question: explain the following terms with the suitable example. Chemoselectivity, multi-component synthesis. First is the multi-component synthesis, an organic synthesis in which more than two components, two reactions vessels involved is called as multi-component synthesis. In the case of the multi-component synthesis, there is decreases in the entropy. Multi-component synthesis are more efficient than the single or multi-stage synthesis in terms of the yield and the economy. Example: multi-component synthesis are the Manish reaction and the Biginelli reactions. Question number 2 is the 1.2 gram of salicylic acid and acetylations gives the 1.4 gram of the acetyl salicylic acid. Determine the theoretical and the percentage yields. So firstly, draw the reactions. Acetyl salicylic acid, salicylic acids, acetic anhydride, theoretical yield, value for molecular weight. We have to find out of the reactant and product also. So after performing the complete test, we get the molecular weight of X and a molecular weight of Y. Then put this value in the theoretical yield. We will get the answer 1.56 gram percentage yield. The actual yield of the product divided by actual theoretical yield of the product into 100. Design suitable synthesis of the following compound: para-iodoxybenzoic acid, butane, 2-all, causing the Grignard reagent. What is the atom economy? Calculate the percentage atom economy in the following reactions. CS3CHI CS3 plus KOH gives the CS3CH double bond CH2 plus Ri plus CH2O. Atomic weight is carbon is equal to 12, hydrogen is equal to 1, oxygen is equal to 16, potassium is equal to 39, iodine is equal to 87. So percentage atom economy is equal to molecular weight of desired product divided by molecular weight of the desired product plus molecular weight of the byproduct. So into 100. So the answer will be the 18.58%. This is all about today's lectures. So remaining part we will cover in the next lectures. In the next unit, natural product, we will start. Thank you very much.